So today we will learn from the examples of last time and try to develop a theory which will allow us to understand how things actually factorize in rings. And to set it up formally, I will go to the more general settings and then define various quantities of interest that we have. Okay, so let's start with a general ring. And as I had said that we will be focusing only on commutative rings. So this is what we have. The first thing, since we are interested in division, that what are the elements that are divisible by what other elements? That's essential. That's the sense of prime factorization of any number. And that's what we want to see happening in this ring. So first thing we need to understand is what are the elements that are divisible by something else. Now, one type of elements divide just about everything. For example, if your ring R is a set of real numbers, in that case every number divides every other number. So divisibility there is very general, and therefore there is no concept of prime numbers there and so on. That's we had seen earlier as well. So it's important to understand first that what are the elements that are that have an inverse present in the ring. Because if an element has an inverse present in the ring, in that case, that element would divide every other element. So let's formalize that. So we say that an element A in the ring is a unit if there is another element B in the ring such that AB is 1, which is another way of saying that B is the inverse of A. Okay. Now, if an element is a unit, then that element, like I said, would divide every other element. Take any element C divided by B is, or C divided by A is same as C times B. So there is a division available with respect to every. So it's only with respect to non-unit elements that we can talk about factorizing them. So let's C be in R be a non-unit. Now C I want to see if I can factorize C into, let's say, C1 C2, that is C, whether C equals C1 C2. There would be C's which I can factorize, there would be C's which I cannot factorize. And that for the case of integers, that is the difference between a prime and composite numbers. So let's give a definition to or make a distinction of these two types of non-units. Okay. So this non-unit C we call an irreducible element. If whenever we can write C as C1 times C2, one of C1, C2 is a unit. Now notice two things which are different here in terms of if you analogy with the integers. In integers, when we define a prime number, we say that whenever C is a prime, whenever I write C as C1, C2, then C1 or C2 is 1. Here we are not insisting that C1, C2 be 1, we are saying that it should be a unit. Do you see a reason for that? There is a very simple reason, that if you say try to mimic that definition, that C1 or C2 is 1. Right, so basically if there are, if a ring has only 1 as unit, or rather in integers case, there are 2 units, 1 and minus 1. If the ring has no other unit, then this definition is the same. Calling it unit or calling it 1 or minus 1 is the same. But if the ring has units other than 1 and minus 1, then we must use this definition. Otherwise, I can always take any C, I can always write it as C times AB, where A is a unit. Okay, because AB is 1, so C is C times AB, and C times AB is equal to CA times B. So I have managed to write C as product of 2 elements, CA and B. Neither of them is 1 or minus 1. So that definition will completely fail to make any useful contribution. So we must have a more general definition, and this is the right one. The second difference is I am not calling C a prime element. I am calling it an irreducible element. And there is a reason for it, which is that prime numbers I would like to keep associated with that unique factorization situation. As prime numbers, we also understand that every number can be uniquely factored as a product of prime numbers. So I want to keep the name prime to be reserved for such structure. In a ring, in general, that structure may not exist, that unique factorization we have seen. So instead of calling such element C in this definition a prime element, we will call it an irreducible element. And once we have this unique factorization, then whatever terms or whatever numbers we have which admit such unique factorization, or whatever irreducible elements which give rise to unique factorization, we will call them primes. Okay. Now, we know that certain rings have unique factorization property, certain rings don't. And two canonical examples are, leaving aside integers, we have z square root of minus 2. This has unique factorization. And z square root of minus 5 does not have. Okay. And the target remains the same. How do we restore or bring in that unique factorization property in all of these rings and more, not just these rings? So this, like I described last time, this problem arose initially. People thought that all such rings have unique factorization. Came up with a problem in terms of for proof of Fermat's last theorem. So then all such rings were relooked at. Some rings had unique factorization, some did not. And there was a mathematician I mentioned last time, Kumar. who was the first one to address this issue, and he wanted to see how can we restore unique factorization. So what he said was that, for example, in z square root minus 5, we have 2 times 3 equals 1 plus square root of minus 5 times 1 minus square root of minus 5. And these happen to be irreducible elements. Now I will use the terminology I just defined. 2, 3, 1 plus square root of minus 5, 1 minus square root of minus 5 are irreducible elements in this ring. So it can't be factored further. What Kumar said was that that is because there are some other numbers into which these numbers factor, but those numbers are not present in this ring, z square root of minus 5. So he postulated these additional numbers and said that these numbers, although are irreducible in this ring, they do factor in terms of these other numbers, and then the unique factorization property holds. So he developed that theory and gave these mysterious other numbers the name ideal numbers. But what are these ideal numbers? I mean, where are they? They are not in this ring, z square root of minus 5. So one has to bring them in from outside. What are their properties? All these sorts of questions arise. What Kumar said was that, look, these numbers are numbers that divide 2, 3, 1 plus square root of minus 5, 1 minus square root of minus 5, for example. Okay. So these numbers are of the kind where they satisfy the typical divisibility properties. What are the typical divisibility properties? That if a number divides there are two primarily properties. First one, that if C divides A and C divides B, then C divides A plus B. And second, if C divides A, then C divides AB for any B. And so he said that these are the ideal numbers which divide the real numbers, the numbers we start with, and they divide, their division satisfies these properties. And then he's developed this theory to show that the unique factorization property would hold when you include such ideal numbers. But that whole thing was kind of unsatisfactory, because you can always ask, where exactly are these ideal numbers coming from? What really is their connection with the actual numbers we start with? It seems to be a little, it seems as if it's been pushed, this concept has been pushed to just fix this unique factorization property. So that therefore was not very satisfactory. Now after Kumar, another mathematician, also very famous, Dedekind. I'm sure you may have heard of his name. Dedekind made a simple change of perspective. And with that simple change of perspective, he could very nicely set the whole thing up. He could reconcile what really means by ideal numbers with and what are the actual numbers, how do they interact with each other, how are they related to each other, exactly how are they coming. Everything was very nicely explained. And it's all followed by a very simple change of perspective, which was the following. What Dedekind said, which I would call Dedekind's view. And since we are interested in, again, divisibility primarily, so his view was treat each number not as a number per se. Of course, it is a number, but he adopted a different view, which is to view each number as a collection of numbers which are multiples of this. For example, take the number 2 in integers or integers. That's just I can view it just as a number 2. Alternately, and that's the Dedekind's view, that represent number 2 as a set of all even numbers. That's because that set is precisely the set of all numbers which are divisible by 2. Similarly, number 3 is viewed as set of all numbers which are multiples of 3. 4 is the set of all numbers which are multiples of 4. So it seems like a very unnecessarily complicated way of viewing a number, which it is in case of integers. But this view helps resolve this mystery of ideal numbers very nicely. So at the cost of introducing this additional complexity, we are able to gain something. So let's adopt that view. Okay. And we give a name to, now this is just one element view, but I'll generalize now. This definition lends itself to a very nice generalization, which is the following. We call a set I, which is a subset of elements of the ring R, an ideal if it satisfies these two properties, that if two elements A, B are in I, then there's some A plus B is also in I. If an element A is in I, then A times B for any B in R is in I. So this set I, actually, if you just go to that divisibility property, precisely captures that. Okay. So the set I therefore is representing some it's a representing a set of numbers which have, let's say, in some nice way it is divisible by one, maybe more than one numbers. That is something that we will see later on. But if you just compare the divisibility property with I, that is precisely capturing it. Okay. And the advantage here is that we then, in the definition of I, we don't have to say that all the elements are multiples of some C. If all the elements are multiples of, say, C, then certainly it satisfies these two properties. But this is more general, and in fact, that difference is very important in our calculations later on. Okay. So, what are ideals of a ring? Let's see some examples. In Z, the ring of integers, all multiples of a number are ideals. So, I will denote this notation A within a brackets to represent the set of all multiples of A. And this notation I will use in general, for general rings, not only for Z. Okay. Are there other ideals in Z? The answer is no. These are the only ideals in Z. And the proof is also straightforward. Take any ideal in Z. There is a smallest number in this ideal I. Okay. Consider the smallest number. Let A in I be the smallest. The smallest, let's say, positive number in it. Now I claim that this ideal is simply all multiples of A. Suppose there is a number which is not a multiple of A in I. In that case, you can write the GCD of, let's say, let that number be B, which is not a multiple of A. Take the GCD of A and B. That's a number smaller than A. The GCD, by extended Euclid's algorithm, if you remember, can be written as A times alpha plus B times beta. Now, since A and B are both in the ideal, A times alpha is in the ideal, B times beta is in the ideal, and their sum is also in the ideal. So that means the GCD of A and B is also in the ideal I, which is a number smaller than A, but that's not possible. So it follows that the ideal is simply all multiples of A. Okay. So in integers, the ideals are exactly, just changing the view, they are exactly numbers. In Dedekind's view, we are identifying number with all the multiples of that number, which is an ideal. And in integers, the ideals are in one-to-one correspondence with numbers. Let's go to a more interesting case. How about z square root of minus 5? See, let's look at this number. 1 plus square root of minus 5, 1 minus square root of minus 5. Okay. Let me consider the following. Let us define an ideal I to be the following. So that's a slightly complex definition. One is in this. One is not in this. 2 is in this. So it contains all even numbers, surely. It contains all multiples or even multiple of square root of minus 5. That's also true. So we can write it, but that's nice observation. We can write it as also as alpha, 2 alpha plus 2 beta square root of minus 5 for alpha, beta and z. Why? Because 2 alpha is in this. So we want to show that any element in this set is in this set and any element in this set is in this set. That you can derive very easily. I don't think I need to explain how to do that. This further, I can simplify it even more. It is 2 alpha plus 2 beta square root of minus 5, where alpha, beta are simply integers. So this is a more presumably restricted set than this. Here alpha and beta can be any numbers in z square root of minus 5. Here alpha, beta are only integers. But it follows pretty simply by the fact, no matter what alpha, beta are in z square root of minus 5, you substitute that in here, multiply it out, collect the coefficient of square root of minus 5 on one side, coefficient of, let's say just the integral part on the other side. Both these numbers would be even. Why? Because everything here is even. You start with, there is a multiplier of 2 here, there is a multiplier of 2 here. So it is 2 times alpha plus beta square root of minus 5. 2 times alpha plus beta square root of minus 5, where alpha, beta are also in z square root of minus 5 is any arbitrary element you can get by this fact of z square root of minus 5. But since there is a multiplier 2 sitting outside, that is makes every component an even integer. Okay, this is not clear? You work this out. I will leave this as an exercise, very simple exercise for you. What is important right now to observe is that this ideal, this is an ideal. Firstly, I have not even shown that this is an ideal actually. Why is this an ideal? And 2 numbers of this form, when you add, they still remain in this form. That's simple. So this is an ideal, and we can simplify this ideal to this expression. Okay. Now, so this is an ideal of z square root of minus 5. Is the next question I am going to ask is there a number in z square root of minus 5? Is this ideal expressible as all multiples of some number a.
3 plus square root of minus 5. So that number is not inside.
3 plus square root of minus 5 is not in this?
Second formation is 2 alpha plus 2 beta under root minus 5.
Mhm.
2 alpha should be equal to 3.
Mm-hmm.
So alpha should be equal to 3 by 2.
Yeah, that's not allowed. Yes.
So that can
So 3 plus square root of minus 5 is not in this idea. Okay. So are you saying that these two equalities don't hold? Oh. Oh, 1 plus square root of minus 5 is not it. So what I've done is wrong, sorry. So let me erase all of this. I had something else in mind that I wanted to show here, sorry. Good that you pointed out. Okay. So let's get back to this idea. Let's just try to understand this. First question, does this ideal contain all elements of this ring? This question is same as showing or is answering the question, is 1 in the ideal I? Because if ideal contains the entire ring, then of course 1 is in the ideal. If 1 is in the ideal, then all multiples of 1 are in the ideal and all multiples of 1 are precisely the whole ring. So is 1 in this ideal I. If 1 is in the ideal I, then we will have 1 equal to some alpha 1 plus square root of minus 5 plus beta 1 minus square root of minus 5, which is alpha plus beta plus alpha minus beta square root of minus 5. Right? So this means alpha must be equal to beta. Oh, elements of z square root of minus 5. Okay. Yeah, I'm treating them as integers, which is wrong. So we'll have to express alpha itself as an element of z square root of minus 5, which is alpha 0 plus, let's say, alpha 1 square root of minus 5 okay, and this I can write as, let's just collect the coefficients together, alpha 0 plus beta 0 minus 5 alpha 1, oops, it should be beta 1 plus 5 beta 1, and then plus alpha 0 plus alpha 1 plus beta 0 minus beta 1. Right. So what is, does this have a solution over integers? No? First look at this. This must be equal to 1. How can this be equal to 1? This is a multiple of 5. Alpha 1 plus beta 1 times 5. And this is alpha 0 plus beta 0. Beta 1 equal to this. Okay.
then the real part becomes even.
Okay, let's do that. That's a good point. So, not this. So the conclusion is that beta 1 equals alpha 0 plus alpha 1 plus beta 0, and 1 equals alpha 0 plus beta 0 minus 5 alpha 1 minus 5 beta 1 That's alpha 0 plus beta 0 minus 5 alpha 0 minus 5 alpha 1 minus 5 beta 0. And that equals sorry, miss something? This one. Say it again. This should be plus. This one? Oh, you can't see it there. Now you can? Oh, you cannot see there. So which are you talking about? So just read out the line. The imaginary part, yeah. Alpha 0 plus alpha 1 plus beta 0. That's correct. And minus beta 1. Minus beta 0. Why would that be minus? Both should be minus. Beta 1 should be plus. Oh, okay. Minus beta 0 plus beta 1. You're right. So beta 1 therefore is, or it's a beta 0. Let me change this to beta 0 to be equal to beta 1, and 1 equals alpha 0, and this is okay. Then let's replace this. Is this, and that's not possible. There is no solution possible because this right hand side is an even number, left hand side is 1. Okay. So surely this ideal contains many elements but doesn't contain one. Now the next question, which is what I am leading to, is that can this be expressed as multiple of some A? Let's assume that. Let's try to work this out. Suppose A equals C plus D square root of minus 5. Then one plus square root of minus 5 is C plus D square root of minus 5 times something else, right? Let's say yes. Both 1 plus square root of minus 5 and 1 minus square root of minus 5 are multiples of C plus D square root of minus 5. Correct? Now let's see what is the best way of arguing this. If we take the norms, the norm on this side would be 6. So C, the norm of this must divide 6. And since this is 6, the norm of these two are the same. Norm of this must divide 6. So let's just see what are the divisors of it, okay? Norm of this is C square plus 5D square. This divides 6. So what are the possibilities? Very few. it could be, D could be 0, and then C must be 1. Then it is fine. Or D could be 1. In that case, C must be also 1. Okay. So if CD is 0, then this is just 1. A is 1, which is certainly not the case. That is, this ring I, or the ideal I, is not all multiples of 1, which is the entire ring. That's not true. We have already seen it. 1, 1 means it is this number itself, 1 plus square root of minus 5. Okay. So 1 plus square root of minus 5, sure, I can write it as 1 plus square root of minus 5 times this. And we are saying that ideal I is simply all the elements generated by 1 plus square root of minus 5. Then we come to this point. How about this? 1 minus square root of minus 5, is it, can it be written as one plus square root of minus 5 times s plus t square root of minus 5? Now, is this possible? See, again, if you go by, take the norm, this is 6, so this norm should be 1, which means s square plus 5t square must be 1, which means t must be 0, which means s must be, well, plus minus 1. So this is just plus minus 1. This is certainly not true. It's false. And therefore, we can conclude so here is an ideal which is slightly funny one. It doesn't quite correspond, if you look at the Dedekind view, this ideal does not correspond to any number in the ring, because the numbers correspond to the ideals which are collection of all multiples of that number. Here is an ideal, it is an ideal, it is in the ring, but it doesn't correspond to any number. So what is this? And it turns out this is what, in the Dedekind's view, this is what Kummer's ideal numbers were. That is, those ideal numbers that he brought in from outside with a certain property to restore the unique factorization property. Once you adopt the Dedekind view, those ideal numbers are ideals of this kind, which are not multiples of a single number. And with the help now, again, keeping with the Dedekind's view, we can write any number. Now, a number in Dedekind's view is an ideal of a certain kind, which is a model. So, any number slash ideal has a product in a unique way of certain type of numbers slash ideals. So I need to define the product of ideals, and they just essentially translate the arithmetic of numbers over numbers to arithmetic over these ideals, which is the Dedekind view. That I'll do next time. And then we can see that everything will focus particularly on this example of z square root of minus 5, because we know that unique factorization doesn't hold here. We know that 2 times 3 is equal to, that is 6 factorized in 2 different ways. So we'll see how using these ideals we can restore the unique factorization property once we define arithmetic over ideals. Okay? And once we understand that, then we'll get it. I'll just state the more general structured theorems for a large class of rings, which are called to honor the work of Dedekind, they are called Dedekind rings. Those are the rings which precisely admit this unique factorization in terms of ideals. Okay, so that's the plan for the next class.